In the 1950s, Union Pacific and General Electric built a locomotive so powerful, nothing in America had ever come close. 8,500 horsepower, a rating that dwarfed every diesel on the continent. On the flat desert stretches between Iowa and Utah, it was untouchable. But this machine had an embarrassing secret no one in the program wanted to talk about. When the terrain tilted upward, even slightly, America's most powerful locomotive could not pull its own weight. And the reason why reveals one of railroading's greatest engineering contradictions. By the late 1940s, Union Pacific steam locomotives were aging fast. Each run demanded large crews, constant maintenance, and long layovers for servicing. The economics no longer made sense. Freight volumes on the Western Main Line were rising, but the railroad's most powerful diesels, like the EMD F7 and Alco PA1, were capped at 1,500 to 2,000 horsepower per unit. To move a heavy train across the desert or through the mountains, dispatchers had to lash up 3, 4, sometimes 5 diesels just to match the output of a single steam giant. That meant more fuel, more crew, and more wear on the rails. Union Pacific's motive power chief, J.M. Miller, saw the limits of this approach in stark terms. In a 1952 memo, he wrote that the railroad needed a new kind of engine, one that could pull 5,000 tons by itself without a string of helpers, and cover the long, flat stretches between Council Bluffs and Ogden without stopping. Miller believed a gas turbine could finally deliver the power-to-weight edge that steam and diesel both lacked. The turbine's promise was simple: massive horsepower in a single, streamlined package, burning cheap Bunker C fuel that refineries were practically giving away. The timing seemed perfect. Post-war refineries were producing more residual oil than the market could use, and the regulatory climate allowed heavy, high-sulfur fuels without penalty. General Electric, fresh from building aircraft turbines, was eager to prove its technology on rails. For Union Pacific, the gamble was clear. If a turbine could deliver 8,500 horsepower in one unit, nearly triple the best diesel available, then the railroad could leapfrog its competitors and retire its costly steam fleet all at once. But the early diesel electrics had already revealed a stubborn reality. Even at their best, they struggled with low-speed torque and couldn't sustain high-tractive effort on grades without multiple units. Miller's vision depended on the turbine's raw numbers translating into real-world pulling power, especially on the toughest parts of the route. The partnership with General Electric began as a bold answer to a pressing need: more horsepower per locomotive, fewer engines per train, and a break from the past. The stage was set for a technological leap, and one that would soon reveal just how complicated brute force could become when the rails turned uphill. The first Union Pacific gas turbines didn't just roll onto the rails, they arrived with a roar. Newspapers called them jet trains and described their entrance as something out of science fiction. At the 1955 unveiling in Omaha, the turbine's high-pitched wail drowned out conversation, drawing crowds who came just to hear and feel the machine thunder past. Union Pacific and General Electric leaned into the spectacle, issuing press releases that boasted of 8,500 horsepower, more than any locomotive in North American history. Company brochures compared the turbines to the mighty big boy steam engines, but insisted the new machines would outclass even those legends, pulling more freight, faster, with a single unit. Trade journals ran glossy spreads featuring the sleek, two-part bodies and massive fuel tenders, painting the turbine as a symbol of American power and progress. Railroad executives gave interviews predicting the end of the multi-unit diesel lash-up. The message was clear: one turbine would do the work of 4 diesels or a whole team of steam giants. The numbers were staggering: 145,000 pounds of tractive effort, 24,000 gallons of fuel on board, and a top speed over 65 miles per hour. For a brief moment, the turbine became a rolling celebrity, trackside crowds gathered just to witness the big blow scream across the prairie. Engineers described the sensation of opening the throttle as like flying a jet down the rails. The promise was intoxicating. A single, unstoppable engine erasing the need for helpers and changing the economics of freight overnight. In those early years, the turbine's myth grew with every public run, feeding the belief that sheer horsepower could solve any challenge the railroad faced. Out on the open stretches between Council Bluffs and Ogden, the gas turbine locomotives delivered on every promise the engineers had made. Dispatch logs from the late 1950s record these giants hauling 5,000-ton trains across the Nebraska and Wyoming plains at a steady 45 miles per hour, barely breaking a sweat. The turbines ran for hours at a time without a hint of strain, their jet-like roar echoing for miles in the empty desert air. Freight schedules tightened, and Union Pacific's operating reports showed a clear bump in average speed and on-time arrivals along these flat corridors. Crews described the sensation of cruising at full throttle as something almost unreal. The cab would vibrate with a deep, steady hum, while the turbine's wail drowned out all but shouted conversation. One engineer recalled the way the throttle responded, smooth, effortless, and with a sense of endless reserve. It felt like you could just keep pouring on the power, and the machine would never run out of breath, he said, years later. The heat from the exhaust sometimes melted the tar at rural crossings, but on these wide-open runs, that was a minor inconvenience compared to the sheer performance on display. Fuel records from this period tell the same story. With bunker C oil costing just 6 cents a gallon, the turbines could move freight at a lower cost per ton mile than any diesel or steam engine in the fleet. The numbers looked unbeatable. One locomotive, one crew, one massive load, covering hundreds of miles without stopping for water, coal, or helper engines. For a brief window, it seemed as if Union Pacific had found the ultimate answer to the post-war freight challenge, brute horsepower harnessed and unleashed across the desert, running farther and faster than anything that had come before. The program's momentum was undeniable. Yet beneath the surface, the very strengths that made the turbine a desert champion would soon become liabilities elsewhere. For now, though, the machine's legend grew with every mile of straight, sun-baked track. June 1953, Sherman Hill. The gas turbine locomotive, freshly celebrated as Union Pacific's new champion, faced its first real test outside the flatlands. The grade ahead was only 1.15%, hardly the Rockies, but enough to separate theory from reality. The GTEL prototype, with a full load of 4,800 tons, entered the climb at 38 miles per hour. Within minutes, the speedometer dropped to 20. The turbine's high-pitched roar faded to a frustrated whine as the governor automatically throttled back, trying to keep the turbine blades from overheating. In the cab, the engineer watched the ammeter needle sink and felt the unmistakable shudder of a train losing its grip. Dispatchers recorded the moment in the operational log. The entry read, "GTEL unable to sustain required tractive effort on 1% grade without assistance." The locomotive's massive horsepower, so impressive on the plains, could not translate into the low-speed torque needed for the climb. The weight of the machine, over 1 million pounds with its fuel tender, became its own enemy, demanding more force just to haul itself uphill. Tractive effort fell to around 110,000 pounds force, far short of the 170,000 needed to keep the train moving. The engineer radioed for help. 2 Alco PA diesels, waiting in the siding at the base of Sherman Hill, were summoned and coupled on. Only with their added pull did the train finally crest the summit. Crew recollections from that day describe a mix of disbelief and frustration. The turbine had been promised as a single-unit solution, the end of helper engines and crew changes. Instead, it stalled on the very kind of grade that defined Union Pacific's mountain routes. The operational log entry became a quiet turning point. The locomotive designed to end the age of diesel lash-ups had just proven it couldn't do the job alone. That field failure set off a chain of technical investigations, forcing engineers to confront the contradiction at the heart of the turbine's design: unmatched power, but not where it counted most. Gas turbines are built to thrive at one thing: running flat out. Inside the Union Pacific's behemoth, the General Electric Frame 5 turbine spun at nearly 3,800 revolutions per minute, happiest when the throttle was wide open and the train kept rolling above 30 miles per hour. At full power, the numbers dazzled. Specific fuel consumption held steady at 0.42 pounds per horsepower hour, a figure that made sense when every ounce of energy was turned into forward motion. But the moment the grade steepened and the engineer had to throttle back, the turbine's physics turned against it. Unlike a diesel, which can squeeze out decent efficiency across a wide range, a gas turbine's appetite for fuel barely shrinks when the load drops. At 70% output, typical for a train grinding up Sherman Hill, the specific fuel consumption shot up to 0.6 pounds per horsepower hour. The turbine still gulped air and burned fuel at nearly the same rate as at full throttle, but delivered far less useful work. The result? Fuel bills that soared just as the locomotive needed every bit of efficiency to fight gravity. The torque curve told a similar story. Turbines deliver their muscle at high speeds, but as the revolutions per minute drop, torque collapses. On a climb, when the train slows and the wheels turn more slowly, the turbine cannot deliver the grunt needed to keep everything moving. The locomotive's governor, designed to protect the delicate blades from overheating, automatically trimmed fuel flow as the turbine bogged down. This safeguard kept the hardware safe, but it robbed the locomotive of power at the very moment it was needed most. William H. Schwartz, General Electric's project engineer, summed up the dilemma in a 1957 memo. The turbine delivers its rated horsepower only above 30 miles per hour. Any operation requiring lower speeds on grades results in excess fuel burn and excessive blade temperature, threatening component life. Every time the turbine locomotive faced a grade, the numbers stacked up against it. What looked like a triumph of engineering on the flatlands became a lesson in thermodynamics the moment the rails turned uphill. The promise of brute horsepower faded, replaced by the hard truth that efficiency is not just about how much power you can make. It is about how well you can use it when the going gets tough. Numbers behind the Union Pacific gas turbine locomotive told a story that no amount of horsepower could hide. With the locomotive and its fuel tender tipping the scales at 1.22 million pounds, every climb became a contest between brute force and basic physics. The promise of 8,500 horsepower looked unbeatable on paper, but the reality of moving that much mass up a grade exposed the flaw at the heart of the design. Railroad engineers use a simple rule of thumb. A locomotive's maximum tractive effort is limited by adhesion. About a quarter of its weight can be turned into pulling force before the wheels slip. For the GTEL, that meant an adhesion limit of 305,000 pounds of force. On level ground, that was more than enough to keep a heavy freight rolling at speed. But the moment the rails tilted upward, the math turned unforgiving. A 5,000-ton train on a 1% grade demands about 220,000 pounds of pull just to overcome gravity and friction. Add in the weight of the locomotive itself, and a significant share of that force was spent hauling the machine's own bulk uphill, not the freight behind it. The heavy fuel tender, loaded with 24,000 gallons of bunker C, was both a strength and a liability. It gave the turbine unmatched range across the desert, but it also anchored the train with dead weight when every pound counted against the climb. Even with all that power on tap, the GTEL often found itself limited by adhesion, unable to transmit its rated force to the rails without slipping. On steeper grades, the turbine's wheels would spin, before the full force could be applied, forcing engineers to call for diesel helpers or risk stalling short of the summit. The calculations were clear. The turbine's own mass soaked up a portion of its theoretical advantage, capping real-world performance well below the headline figures. In the end, the GTEL's power was trapped by the very weight it carried, a mechanical contradiction that no amount of optimism or engineering spectacle could resolve. The verdict was sealed not by lack of ambition, but by the hard limits of adhesion and gravity. This was a lesson that would haunt every attempt to turn raw power into practical traction. The entire economic case for Union Pacific's turbines rested on one number: the price of bunker C oil. In the early 1950s, refineries treated this heavy, tar-like fuel as a waste product, selling it for as little as 6 cents a gallon. That made the gas turbine locomotive's appetite for fuel look like a manageable expense, especially when compared to diesel. But in the summer of 1956, the Suez Crisis turned that logic upside down. As tankers were rerouted and global oil markets panicked, the price of bunker C doubled almost overnight, climbing to 12 cents a gallon by the end of 1958. Suddenly, every mile the turbines ran cost twice as much in fuel. The numbers on the balance sheet shifted from black to red. On a flat run, moving 5,000 tons over 100 miles now cost $139 in fuel instead of $66, an increase that wiped out the supposed savings over diesel. On grades, the cost per ton mile nearly tripled, as the turbines burned even more fuel just to fight their own weight uphill. Union Pacific's finance office tracked these swings month by month, watching as a locomotive designed around cheap fuel became a liability the moment the market changed. The turbines had been engineered for an era of surplus, but the real world refused to cooperate. The economic advantage, once so clear, vanished in a matter of months, leaving the railroad exposed to the full volatility of the global oil trade. Inside the shop, the turbine's legend faded fast. Mechanics faced a machine unlike anything else on the rails, one that demanded skills more common in an aircraft hangar than a railroad roundhouse. Turbine modules had to be pulled and inspected every 7,900 hours on average, less than half the interval of a standard diesel engine. The hot section blades, exposed to searing temperatures and fine ash from bunker C, wore down quickly. A single overhaul could tie up 30% of the shop's skilled mechanics for days. Crews logged 210 hours on a typical turbine rebuild, with specialized tools and GE-trained technicians flown in for the toughest jobs. Routine tasks such as blade inspection, combustor cleaning, and high-pressure pump overhauls became a steady drain on manpower. Shop dwell time crept upward, with turbines spending 15 to 20% of their operating life out of service, compared to less than 7% for diesels. Infrastructure costs mounted too. Heated fueling stations dotted the desert mainline, each built to keep bunker C flowing in winter. Ash-handling pits and exhaust shelters sprang up wherever the turbines stopped, adding millions to the program's bottom line. The promise of unstoppable power met a reality of constant downtime and hidden expense, quietly undermining the economic case that once seemed so bulletproof. Diesel locomotives didn't win by brute force. They won by solving the real problems the turbine could not. By the early 1960s, engineers had quietly transformed diesel technology into something far more adaptable. Alternating current traction, first tested in prototype units, allowed diesels to grip the rails with up to 0.38 g of adhesion, meaning more of their weight could be turned into usable pulling force, even at low speeds. Multiple unit control let a single engineer manage a string of locomotives from the lead cab, distributing power along the entire length of a heavy train. This approach tamed the grades that had humbled the turbine, keeping trains moving steadily where a single massive engine would slip or stall. The numbers told the story. Modern diesels matched or exceeded the GTEL's tractive effort, but did it with lighter units, lower fuel consumption, and less downtime. Alternating current traction motors delivered full torque at a crawl, while microprocessor controls kept wheels from slipping long before the turbine's mechanical governors could react. Distributed power meant that 5 diesels, spaced throughout a mile-long train, could keep thousands of tons rolling up Sherman Hill without drama or delay. Instead of betting everything on one giant machine, railroads found that a team of smaller, smarter engines could outpull and outlast anything the turbine had to offer. In the end, flexibility and efficiency, not just raw power, decided the future of American freight. The ultimate irony remains: unmatched muscle, yet stopped by its own weight. In engineering, raw power means nothing if it cannot meet reality on the steepest grade. Today, as railroads eye new turbine concepts and advanced materials, the lesson lingers: promise does not guarantee progress. Could modern technology finally bridge the gap between ambition and terrain? The answer still waits, just beyond the next hill. Share your thoughts in the comments below.